Hello everyone, I'm Maruf. Welcome to my presentation. I'm here to present a research paper. The title of the paper is Engineering Parallel Algorithms for Community Detection in Massive Networks. The authors of this paper is Christian Stodd and Henning Meyer-Henke. The main issues that we were worked in this paper is how to detect community in the networks, especially in massive networks, apply parallelism in the existing algorithm. That's why we need to choose the best algorithm. And at last, we compare our result with the existing result that get from the existing method using the existing method. So we need to know why community detection is an important problem in computer science, and why we need parallelism in this particular matter. So first we can see that what is the most uses of this community detection in our society. We can see that we can use this approach in rank manipulation, and we can also use this to discover scientific communities in public databases, and it also uses in the cancer research to identify functional groups, to organize the content on social media sites. So these are the uses of this community detection. There are also other uses exist. So we can focus in the main motivation of this paper to detect the community detection in the social network. So we need to, if we want to use our social networks or any kind of networks, we need to transform the graph data into useful information. And most of the graph is structured application size are huge nowadays, and very few parallel code exist to handle these kind of issues, and most of the existing algorithm are failed to do their job properly when the node size is billion. So we want to perform our contribution towards this problem. There is lots of algorithm exist towards these issues. Actually, then we are going for the best to algorithm that handle this problem perfectly, and the methods are level propagation and Leuven method. So we are going to approach our parallelism in these two methods. So we named our algorithm as parallel level propagation or PLP, and other one is parallel Leuven method or PLM. So if we see that what is going on in the PLP or parallel level propagation. So the uh, so the level propagation algorithm originally introduced by the Raghavan. And in this algorithm, we are going to assign a unique level for every node initially. And we are going to have to perform iteration over the nodes. And in each iteration, every node adopts the most frequent level in its neighborhood. So that the densely connected groups will be in the same level, and this method will continue until we are going to get a stable situation. So we need to contribute in this method to perform its to enhance its performance. So that's why we are trying to use this algorithm in the weighted graph, and instead using the frequent level, we are going to use the dominant level of its neighborhood, and we are going to use a threshold value to termination of this algorithm. And in our case, we are going to use n into 10 to the power minus 5 as a threshold value, where n is the number of vertices. And obviously we are going to apply parallelism in every iterations. And the other method, parallel Leuven method, or PLM, the algorithm is initially introduced by Blondel, and it is a bottom-up multi-level algorithm. And in this method, we are going to use the modularity functions. Then in every iteration, we try to move a node to its neighbor community, and based on their modularity difference. If the modularity difference is increased, if we moved a vertices to its neighbor, then we'll continue the moving portion, and this is called the moving phase actually. And after moving the nodes to its neighbor community, we are going to apply the quotient and we are going to shrink our graph. So in that case, we are going to treat a community as a vertex, and we are going to apply the same PLM method recursively again and again. So we are going to find to forming a communities of communities, and this method will continue until we are going to get a stable situation. So the main contribution towards this algorithm is that we are going to use a shared memory parallelization to PLM, and node moves are evaluated and performed in parallel instead of sequentially. We bring out some refinement in this method and we call it parallel Leuven method with refinement, or PLMR. Now we are going to talk about the technical approach of this algorithm. First, we are going to talk about the PLP, or parallel level propagation. In this algorithm, the input will be a graph. It will include vertex set and edge set, and the result will be a community set. And the community set will contain all the vertices. Initially, we are going to assign a unique level to every vertices, and this for loop will doing handling this situation. And we have a flag updated. It is an integer flag or long flag that will handle the uh, how how many iteration it requires to perform the update our community. So initially we are going to assign the number of vertices, and the active set will be the all vertices. And here is our first condition is updated is greater than theta. Theta is our threshold value, and we are in our experiment we are using n into 10 to the minus 5 as a threshold value. So it is constant value for a particular graph set. And then initially we assign updated as a 0. Here we are going to apply a parallel for loop for the vertices in the active vertices, and we are checking that if the vertex degree is greater than 0, if it has no neighbors, that we should not perform any kind of performance, because it has no chance to fall in the other community. And then we're going to check that the dominant level towards its neighbor vertices, and we are going to be find the L star from that. Then we are going to check that existing community is belongs to the our L star. If not, then we are going to assign the vertex v to that community, and we are going to the update our updated flag as 1, because we are updated one vertices for their community. And we're going to assign our neighbors of these vertices to the active set on the other condition that we are if you see that there is no updated in the level of the vertices, then we don't need to iterate it again and again. So we are going to exclude the vertices from the active set. So that's it, the parallel level propagation. In the PLM or parallel Leuven method, there is a two portion. One is move phase and one is the basic algorithm. So if we look at the basic algorithm first, that we can see that it has an input graph, a vertex set and edge set, and it will output the community set. So initially we are going to apply a singleton to graphs. The singleton means that we are going to assign each vertex is to a single community, and then we're going to perform the move move method to the graph and our singleton community. So if you look at the move algorithm, then we see that we have a two input, actually a graph and a community set, and it will output the community. So in here we can see that we are using parallel for loop again towards the vertex set, and we are going to see that we are going to find out the modular difference in the existing community and towards the neighbor community. So what will happen in here, that we are going to check if we are if you move you from its existing community to the its neighbor community, is there any difference in modularity? If the modularity difference is increased, then we are going to perform the moving the vertex u to the community. In here we can see that we get the community which are the maximum modularity differences. So we are going to apply these phases until there is no change in the community. So if you come back to the main algorithm, you can change that if there is a condition if the community is changed. If changed, then we are going to apply coercion. In the coercion, it will do that. It will treat particular community as a single vertex, and it will shrink the existing graph to the new graph, and it will recursively apply the PLM again to the modified graph. And in the prolonged version method, we are going to stretch out the quotient graph to the normal graph, and it will return the output of the community. That's it in the PLM method. So we are going to show you that we have another type of PLM or parallel looping method with refinement. The difference between the existing PLM and the PLMR is that we perform one more move method in here. So sometimes it will output the more accurate community regarding to the previous PLM, but it will cost more time than the existing PLM. So if you see that the result set we are getting from the applying PLP and PLM in a UK 20705 graph, it is a big graph around 60 million nodes, and we are using a 1 to 32 threads actually. Then our physical um, machines has 16 cores. So if you see that there is factor 8 speed up in if we are going to use the 32 threads in a 16 core processor regarding to the sequential method. So there is lots of speed up in the output to using the parallelism. I think it's a great result towards the community detection in the massive networks. Thank you so much. Any questions?